So remember, to make a buffer solution, you need a acid and a base, and they need to be in equilibrium with each other. So we need an acid and a base to counteract any additions of acids or bases to a solution. So when we look at this, the answer one is kind of the classic buffer solution, where it is a weak acid and its conjugate base. So we have both of these, an acid and base solution, and they are in equilibrium with each other. So number one would make a good buffer. We don't talk about it so much, but you can use a weak base and a conjugate acid. So if you see, we have the base, we have the acid. Because they're weak, they're in equilibrium with each other. Strong acid and strong base does not make a buffer solution, mainly because there's no equilibrium. There's no going back and forth. Remember, with a strong acid and a strong base, we go all the way to the right. And the same thing here with a weak acid and water. Water is not making really particularly basic, so this will not create a buffer solution. So for question one, the answer is 1 and 2, or answer E in the multiple choice. So when we're looking at equilibrium here, and this is something I want everybody to make sure to know, is that in an equilibrium, be it an acid or a base, there is an acid and a base on both sides of the line. So when we talk about a Bronsted-Lowry acid and base, on both sides of the line there is an acid and a base, and those are all in equilibrium. So remember, there's a forward reaction and a reverse reaction. So we tend to talk about things in terms of acids and bases and conjugate acids and conjugate bases, but it's important to know that there's actually 2 acidic species in this equilibrium and 2 basic species in this equilibrium. So I'm asking you, which ones are the acids? So I look at this, and you kind of, what I like to do is look at the products and see that OH minus is a product, so that's definitely a base. So whenever I see hydronium H3O plus, that's an acid. Whenever I see OH minus, that's a base. So if this is basic, if my hydroxide is basic, then this other species, ammonium NH4 plus, must be the acid part of it. And then I remember that the link between a acid and its conjugate base is by the difference of 1 hydrogen. So here, when I remove a hydrogen, so remember NH4 plus is acidic. When I remove 1 hydrogen, that must make ammonia basic. And then the same thing is true here. When I take hydroxide and I add an acid to it, I go from OH minus to H2O plus. That means water is actually acting as a base here. So there's a few different ways of looking at this. I can remember that ammonia is a weak base, so that means water is going to be acidic. But the idea is, there's an acid and base on both sides. On the right-hand side of the arrow, the acidic part is ammonium here, NH4 plus. On the left-hand side of the arrow, the acidic part is water. So our answer is E here. So this is another very important idea that I want people to learn. This is one of the biggest basic concepts that we talk about in terms of the titrations. So we compare the titration of a strong acid and a strong base, and a titration of a weak acid and a strong base. And one of the main points that you got to remember is what's going on at the equivalence point. So when we've added enough base to completely neutralize the acid, and that was one of the key differences between the two. So here, the pH at the equivalence point of a titration of a weak acid and a strong base, the pH is going to be greater than 7. The reason why is, at the equivalence point, we've completely converted all of my weak acid to its conjugate base. The conjugate base of a weak acid actually has a Kb reaction, so that will react with some water and create a small amount of hydroxide. That will cause our pH to be slightly greater than 7. Remember, for a strong acid and a strong base titration, the equivalence point, the pH, would be equal to 7. So that's the big difference. Strong acid, strong base, equivalence point, pH is equal to 7. Weak acid and strong base, at the equivalence point, the pH is greater than 7. So what actually is going to be the pH depends on, the Ka of the acid, so that'll change a little bit, but we know it's going to be greater than 7. So here, which of the following are considered a strong base? So I'm going to send out a sheet. Your ability to look at something and say, is it a strong acid, strong base, weak acid, weak base is crucial, because how we do the calculations on various things after that depends quite a bit on that idea. So remember, strong acid, strong base, no real equilibrium. weak acid, weak base, there is an equilibrium. So being able to tell which one is which is vital. So when I think of a strong base, we defined it as being the the hydroxide of a group 1 metal is the main one. So group 1 metals are the column all the way to the left on the periodic table. So you get like sodium, lithium, and potassium. So when I look at this, I get lithium hydroxide is a strong base. So this disassociates 100%. It's going to literally put hydroxide into my solution. Kind of the tricky one here is iron hydroxide, and we'll talk about hydroxides later on. But this is actually an insoluble salt, and that's the big difference. When I put lithium hydroxide into solution, lithium makes lithium hydroxide here a soluble salt, and so that means it's going to disassociate 100%. It's going to, for every 1 mole of lithium hydroxide we put into solution, it's going to put 1 mole of hydroxide in solution. And that's because it's a soluble salt. So everything with any hydroxide made with a group 1 metal is going to be a soluble salt, and therefore it's going to be a strong base. Iron 3 hydroxide is not a soluble salt. So when I put iron 3 hydroxide into solution, it only disassociates a little tiny bit. So this gets into the idea of solubility products, which is in chapter 20. So if I put in 1 mole of iron 3 hydroxide into solution, only a very small amount of it will disassociate into making hydroxide. So even though there's an OH inside of there, it does not follow our definition of a strong base, which is a hydroxide directly attached to a group 1 metal. And down here in the end, I will tell you, this is one of my more favorite questions on exams, or some variant of that. You just need to know what are the strong acids and weak acids, and you need to be able to pull them out of a lineup. So I love doing this, where I just give you a list of acids, and it's up to you to tell me which are the strong acids. And so I sent out a sheet where I summarized that, and I gave you a list. Yeah, there's a lot more strong acids in the world, but the ones that I gave you are the most prominent ones. So HCl, strong acid. HF is a weak acid. So you just need to know that. HBr, strong acid. HClO4, strong acid. HNO3 or nitric acid, that's a strong acid, and these last two are weak acids, or so you need to be able to pull these out of a lineup. So the only ones I expect you to know are on the ones in my notes, and then I've summarized those into a sheet. So the ones that are on that sheet are the ones that you need to know for the exam.